That one's yeah.
Too much hair.
No.
You didn't practice this bit.
What the hell?
Yep.
Definitely too much hair. So I'm going to be talking about what happens to students before they start writing formal contracts and are absolute beginners from this wonderful book. And Robbie and Matthew and Matthias are all here. This is a book designed to teach absolute beginners. And I especially want to talk to those of you in the audience who may, as I may have grown up in a different neighborhood where there are perhaps fewer parentheses and more types. This is quite a nice neighborhood to move to. And so what I would really love to be able to say is that I can tell you how to teach, how to design programs. It turns out you can't really fit that information into a 12-page ICFP paper, but I have been able to fit an awful lot of tips and tricks. And what I'm going to do is just spend about half the talk saying design programs. What is the design method that is behind that? I'm going to give you a few snippets of things in the papers, what students find difficult, talk about the technology of Racket and the teaching languages from a point of view that I don't think you would get from the creators, and tell you what I think is the most important open problem in teaching this pedagogy. That's unpleasant. The paper contains all of my most embarrassing mistakes, which I am willing to write about in public but not talk about in public, and then much more of these kinds of details. So this is a course in systematic problem solving. It's not a functional programming course, and I want to start by sort of reviewing the problem solving method. There's a design process, and I've revised the design process a little bit to make it work better for my students. It starts with looking at the world and seeing the data. So Phil, a concrete example, if you're in the Department of Motor Vehicles, you can sort of see there's a counter and there are people on one side and people on the other. You can say, there's a queue and a set here, but students can't do that. And so we start with students saying, well, how do we write down the data that's in the world? And all of this is from functional programming. You have your product types, sum types, arrow types, base types, a little bit of polymorphism. All of your familiar technology translates very directly. And so we can teach students to write type definitions. But of course, bare definitions are very hard to understand. So those definitions are illustrated with examples of the data in the world that they're trying to describe. Once they've got that, then they can start designing functions. And so we'll talk about describing the functions, and we'll give the function a type signature. No formal contract, just a very informal purpose statement. This is what the function is supposed to do. And then once again, illustrate that with examples. Now we've got a plan. We're ready to start writing the code. The types are going to come into play again. We're going to look at the inputs to the function and create the function's overall structure. And then the last coding step is to say the types told me kind of the bones of the structure, the function. Now I'm going to put some flesh on the bones, and I have some code. I can test it. And then the step that I've added is really go back and look at your work carefully. Does the purpose statement, the description you wrote for your function, is it really consistent with where you wound up? And more generally, does the code you wrote look like the things that we want good code to look like? So this is the method that students are learning. I'm going to talk about a couple of parts of the method that are difficult for students. But before I do that, I want to show you an example, at least, of these early steps. So I'm going to leap straight to some data examples. This is a data structure that we did, a 2D tree, for finding points in two-dimensional space. And over on the left, I've got an example that says a tree can be made with a vertical boundary. You've got left subtree, right subtree containing some points. Or a tree can be made with a horizontal boundary, and above subtree, below subtree, and again some points. So those are the examples. I've flipped the order. Here is the data definition. I'm going to start with just a point. A 2D point of A is a structure, that's the word for product type. It's got XY coordinates and a value of type capital A. So you see that we have a little bit of parametric polymorphism here. It's okay even for beginning students. Then the tree is a value of some type. You've either got a point or the vertical and the horizontal boundaries that I showed you. And here in the lighter colors are all of the side conditions and invariant that make it an absolutely proper 2D tree search structure. So with the data description and examples, we're now ready to design functions. And here's a function from a relatively late homework that says, if I look at the point marked at the red X, and I'm looking at that place, what is the point in the data structure nearest to that place? And here I've got a functional example. The nearest point is L. And in my functional example, I've grayed out the left subtree entirely. That's because I can reason to say, oh, on the right side, the closest point is L. L is closer than the boundary, so nothing on the other side of that boundary could possibly be relevant to the question of what's the closest point. And this is the kind of reasoning that I want students to get to by the end of one semester of instruction. So they can take a piece like that and build something more complicated. This is an interactive map of the northeastern United States. It shows all of the hospitals in that area. And if you're driving one of Kathleen's cars and you get in an accident, the 911 dispatcher can say, okay, where's the car? And let's show the dispatcher the point of the nearest hospital. So that's the kind of thing that, that students are doing. Let's now look at those preliminary coding steps so that we can have a basis for understanding what's difficult. So this is the nearest point function. Here's its description, its type signature. Takes an XY coordinate, a tree, and gives back a point. And the purpose statement says that it's going to efficiently find the point in the given tree closest to the given XY coordinates. And that's the sort of starting point for getting ready to create that function. Lots more functional examples like the one that I showed you, and I'm now ready to move on to the template, which is shown down here in gray. For the template, I'm going to choose one of the inputs, and that has to be done carefully, but here the choice is pretty easy. Numbers are not very interesting. There's a lot of structure in the search tree, so I'm going to scrutinize the search tree and say, oh, this is a value of some type. It could be a point, a horizontal boundary, or a vertical boundary. So I need to do a case analysis. I'm using McCarthy's con from Lisp. That's the Haskell or Mail programmers in the room. You can sort of think of that as a case expression. I'm going to say, if you're a point, I'm going to have to look at you, and you are the nearest point, so I've just knocked that case off. If you're a horizontal boundary, what am I going to do? Well, I'm going to look at the parts of the horizontal boundary. So I've got a sum of products. I'm going to look at the elements of the product, get the above subtree, the below tree, the location of the boundary. And then I'm probably also going to look at the X and Y coordinates of the search position. And somehow, I'm going to have to combine all of that in the answer. And in this, find an answer. In the student's development, that somehow is going to mean the creation of a helper function. And then I have a third case for the vertical boundary, and it's structurally similar. So that's as far as I want to illustrate to you the design process. And now I want to move on and talk about how do students interact with this? What's it like to use the technology? So here they are in our lab in the evening working on my homework assignment. Why are they all working so hard? What's difficult for them? The first thing I want to mention, and this surprised me, this type-driven development, going from the types of the inputs to the structure of the code, is actually quite hard for beginning students, even though the rules are very mechanical. So if you have atomic data, like an image or a number, there's nothing you can do with it other than pass it to a library function. If you've got a value of subtype, you do a case analysis using cond. If you've got a value of product type, you pull out the elements using selector functions. And of course, if somebody gives you a function, all you can do with a function is apply it. So I thought, oh good, mechanical, easy. This is not what happens when the students actually turn in the code. And there are a lot of flaws. I discussed it some in the paper. The one that I'll mention here is that When you give them a value of sum or product type, they tend to look at it over and over again. I'm going to make the same case analysis or extract the same elements from the same product, usually in a bunch of different functions. So this is something that's hard for them, and they need help to learn how to apply this process. I found that a bit surprising. Something else that's hard that I think won't surprise anyone who's taught students is that it's really hard for them to write good purpose statements. We have a 4-course programming sequence. I've taught 3 of those 4 courses. This is hard for students at every level. And I don't want to show you the worst purpose statements from the beginning students because they would take a very long time to explain to what went wrong, but trust me, they're bad. Here are some that are pretty good. Meters to English. It takes a number, produces a string. The purpose statement says input the distance in meters and then convert them to English. That would be English feet, miles, inches, furlongs. But you can't write the function based on that purpose statement. You don't actually know what it's supposed to do. Here's another one that's a bit better. Move big hand function from time to time. Adds 1 minute to the time structure. So here's a student whom I'm convinced has been corrupted by his primary education with imperative programming languages or other ideas about mutation. Same student who's moving the big hand, so 5 weeks later has got a much better handle on things. The stations on railway is a one-dimensional search structure for finding stations on a railway. As I want to know what are all the stations, the student says return an ordered list of all stations on the railway, southernmost first. So now this purpose statement is almost perfect. I would have liked to see its stations on the given railway, but that's really quite good. So getting to this point is why I wanted to have a sort of step after the work looks done. Please review your work and refactor it to make it good. And we can get to it someplace. So you might be thinking, how could this possibly work with purpose statements like this one? How can the students get anything done at all? I see Matthias smiling in the back because he knows the answer. They look at the code. They just go right past the abstraction barrier and say, oh, well, I don't care about this purpose statement. Let me just look at the body of this function and then I'll know what it does. This works right up to the point where they start writing recursive functions. And I don't know whether it's hysterical or depressing to see them in the lab talking to each other saying, okay, so we have the function, and then it calls itself and it does this, and then it calls itself and it does this, and then it calls itself and they're very aggressive, they're inlining mentally, and after 5 or 6 steps, they blow their mental stacks and they sort of look helpless and unhappy. So what's going on? They haven't learned to trust the purpose statement and not look at the code. And of course, the reason they haven't learned that is because the purpose statements they write aren't very good, so they're not trustworthy. They have to look at the code. So this kind of is a vicious cycle. And it's our job as teachers to turn that into a virtuous cycle where they can say, oh, now I know that I can write a good purpose statement, and then I can trust it, and I don't have to look at the code. So this is not a new pedagogical problem, right? We had this problem in the 1960s, this procedural abstraction, and it's hard. And it's hard for beginners, it's hard for second semester students, it's hard for 4th semester students. It's just something that we have to work at. So a thing to be aware of. I'm going to move on now and talk about my experiences, and more importantly, my students' experiences using the technology, the teaching languages, and the Dr. Racket programming environment. So you may have read some of these nice papers about the structure of the computer science curriculum and language levels and this sort of these nested Russian dolls, and students advance to bigger and bigger languages. And I was always kind of puzzled as to how you design the language levels and how you figure out which ones to use when. And in the end, I didn't really feel that I needed 5 language levels, and I certainly didn't use all 5 language levels. So I want to give you a sense of the space. Way up here in gray are very big, complicated things that aren't shown to students at all. And sort of on the left, I have ideas, on the right, I have languages. So full Racket embodies lots of schemish ideas, and students stay far away from it. And as we go down, we get to things that are simpler and simpler by applying good ideas about how to teach students. And the first good idea is just let's give students a simple language. So The advanced student language is a nice, simple, impure functional language that students can learn. I actually did not use it because I didn't want to teach mutation. So as high as I got in this layer was the intermediate student language, which is a nice, simple, pure programming language. And purity has all sorts of wonderful effects, including simplifying these purpose statements that are so difficult for the students to write. So this is a really, I wrote all of my code in intermediate student language. It's a perfectly nice programming language, quite small. There's a couple of more little layers in there that I'm not going to talk about. And then the very beginning, the bottommost layers, I like to think that I could have thought of designing a language for students that was simple and pure. But down here is something I never would have thought of. And when I first encountered it, I thought it was crazy. It's like you're giving students a language with no local variables, no let-bound names. All they have is function parameters? This isn't a programming language. What are you doing? So it turns out that what we're doing is we're essentially militating very strongly towards having students write helper functions. If there are no local variables, it's really hard to write those awful, huge functions that those of you who've taught beginning students have seen beginning students always like to write. So this is absolutely brilliant and has a tremendously good effect on their early habits. And so this is my views. These are the two language levels I care about, and the story I care about is no local names, purity, and that's really it. Let me talk a little bit about our students' experience with Dr. Racket. This is the GUI IDE. It was not so good. I think part of the problem is, as far as I can understand, the students are given the exact same programming environment that the full Racketeers use. They get the full Racket help system. Within a couple of clicks, they get to full Racket documentation. They don't understand it. My teaching assistants don't understand it. So this is not a good situation. There's also buttons they can click that cause Dr. Racket to go away for a few seconds. And then when it comes back, the code is sort of all lit up with bubbles and arrows and colors and things. And this is also not helpful to beginning students. So I would be disillusioned, except for one thing. If you use Dr. Racket, you cannot compile your code without testing it. You can, but it shows up in giant black reverse video, and everybody in the room can see that you haven't tested your code. And if I do it in the classroom, they can see that I haven't tested my code. They call me on it. And this is fantastic, right? The students think that testing this stuff is absolutely essential. So we didn't have to sell them testing. It's that they don't just think that it's normal to test, I guess we'll do it. They think this is great. And so this is a huge win, and I'm willing to put up with all the nonsense and the mystery in order to get this testing everywhere outcome. The last piece of technology I want to talk about is something called world programs. A very nice paper from ICFP 5 years ago. Students build interactive graphics applications by composing pure functions. And if you read the paper, there's a sentence that says that this is nice because students can build programs that are like the applications that they use on their computers. And this is true, but I think it sells a technology way short. There's much more important things about world programs. So think about the Department of Motor Vehicles example. I can't bring students to Department of Motor Vehicles, show them what's going on, and say, implement that. But I can give students a demo of an interactive application where I'm clicking the mouse or moving circles and drawing line and say, think about implementing that. And that's a place where they can start to develop this skill of, let's look at a simple world and look at the data, define the representations. Let's look at a simple behavior and figure out how am I going to decompose that into functions. And this is pretty important because a lot of the design methods is sort of aimed at a single function. Here's a chance to say, all right, multiple functions working together to solve a problem. And the combination of these two means that the decisions that students make have consequences. And if they make bad decisions, the code doesn't work and it's terrible and they can't debug it. And if they make good decisions, the code is clean and it's fun to look at and it does work. And so this really kind of gives them a sense that they're starting to be in charge and not just doing what I tell them to do. So this the world programs are really worth a close look and deep thought. So to wrap up, I want to talk about this important open problem that we ran into, and that is simply, what do we do with the code that the students give us when they're done? How do we judge it? How do we evaluate it? As an instructor, I really care about only one thing. Is this code the result of a systematic process of software development? That's what I'm trying to teach. But what do I do with that question? Do I say, yes, systematically developed it. You, sir, have earned an A. No, not systematically developed. You, sir, have earned an F. Well, as a practical matter, I can't do that. I have to have some shades of gray. So I went around, I talked to all the more experienced instructors I could find. I said, how do you grade this stuff? And the answer I got back was very disappointing. People say, okay, I've got an assignment, it's worth 20 points or 100 points. And then they have these big schedules of point deductions. So there's a couple of problems here. I don't know what a student is supposed to learn from having points deducted. And more to the point, I have no idea how to create my own assignment. How do I create a schedule of point deductions? What do I do with that? So in my mind, this is a really important problem that I'd like to see our community work on. How do we judge the shades of how systematically something is designed? And maybe there's something in primary trait analysis that we could look and see what are the traits that are systematically designed, sort of partially systematically designed. What are the hallmarks? Open questions, we don't have the answers. So I'm hoping I'm going to encourage you, especially those of you who, like me, grew up in a different neighborhood, to go out and try this stuff. I believe that this course and the book and the pedagogy totally deliver on the promise of effective problem solving. My students who chose to go on to our second course, which by the way is taught in C++, they did quite well despite having absolutely no staff support for the transition or anything else. They sort of went in, they were a bit disappointed at the tremendously bad unit testing for C++. Equally important, for those of you who've been professors for a while, this is easy to sell. Nobody is willing to stand up in a faculty meeting and say, I am opposed to teaching students systematic methods of software development. So that's really great. Functional programming is never mentioned in any of the faculty meetings. But functional programming really matters. Right? The technology helps. The teaching languages are fantastic. Dr. Racket is a mixed bag, but the unit testing that's built in is fantastic. And there's all sorts of good functional programming stuff underneath. I got to use all the stuff that I learned from years of ML and Haskell, and it's great fun to teach. So please dive in. And it's not perfect yet. I'm sorry, Matthias, but it can be improved. Yes, the contract says that it's Robbie's fault that this pedagogy is not yet perfect. There are plenty of open problems to work on besides this assessment problem, and I hope that some of you will be inspired to come in and participate, and that at future ICFPs we'll get to see more papers like this one.
We have time for one question.
Microphone? Say your name?
I will solve the open problem.
Yeah, you said that before.
They didn't listen. So that was my follow-up question. The design recipe, not just the one that you show, but all the design recipes actually suggest exactly how to assess a student's progress. Without a design recipe, a teacher cannot assess the progress that a student makes toward the solution of a problem. With a design recipe, you have 6 intermediate products. You can assess every single one of them. In particular, on homework assignments, and in lab assignments, and in exams, you can actually therefore test individual steps. You can say assignment, problem number 3 is only about purpose statements. Assignment number 4 is only about designing examples for a given purpose statement. And for each step, you can assess what's going on. So yes, you cannot maybe judge the entire thing, but you can check on students' progress towards solving, toward individual steps of systematic design. What is left open with that approach is the integration. Okay, I accept that, and I will sit down with you and we'll figure it out. But 60% of the problem is solved.
Yeah, I agree with that.
All right, thank you very much.